Why do rockets make that crackling and popping sound? If the Earth spun faster, would it be easier to launch rockets? And what's the best way to photograph auroras? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just go to the YouTube comments, write it down. I will gather a bunch of them up and I will answer them here. All right, let's get into the questions. Even Rose. When watching rocket launches, I'm fascinated by the crackling and popping sound of the engines. Does it sound like that in real life, and what causes this sound? So yes, it sounds like that in real life. And in fact, the recording that you hear from NASA and SpaceX and so on doesn't do it justice because it sounds very high. Like you're hearing the rocket launch, you're hearing this kind of crackly poppy sound, and you definitely hear that. But there's another part of the rocket, and that is the sort of sound waves that are coming at you. And so when you see a rocket launch, and I've seen one, I watched the OSIRIS-REx mission launch, and I'm sure Chad has got some beautiful B-roll that he's going to play right now. We were several kilometers away from the launch site, and the rocket takes off, and it's silent, right? It's flash, you see it's silent as it's starting to go up. And then a few seconds later, you can see this sound wave moving across the bay as the sound is making its way towards you. And then as soon as it does, you hear all of the sound, that crackly poppy sound as the thing is taking off, but then you feel it. You feel sort of the pressure on your chest from the sound waves slamming into you one after the other. So what's causing that sound? So the way a rocket works is that it is expelling exhaust gases out of the back of the rocket. And thanks to Newton, we know that if you throw things out of the back of your rocket at high velocities, then you're going to get a kick in the opposite direction. And the only way to get the most efficient system is to fire those exhaust gases out at incredibly high speeds. So you're seeing the exhaust gases come out of the rocket between like 2,500 and 4,000 meters per second. It depends on the fuel, if it's a solid rocket motor, if it's a liquid rocket, whether it's methane, whether it's liquid oxygen and hydrogen. I mean, they all just kind of change, but just in general, these are going really fast. And so they are moving faster than the speed of sound when they are coming out, and they are immediately producing shock waves, sound, because they are going at supersonic speeds, and all of the different bits and pieces of gas are coming out and they're interacting with their sound. And you're just getting this cacophony of cracks and pops. And it is an unbelievable experience. And I've mentioned this in previous videos. Like if watching a rocket launch is on your life list of things to do, it's a relatively easy thing to knock off that list, that you can go out now to Cape Canaveral. It's a great place to take the kids. You can see all of history's great rockets. And then you can stay at a place like, say, Cocoa Beach. There's hotels right there on the water. You get a nice hotel on the water, and SpaceX is launching rockets almost every week, sometimes within 24 hours of each other. And so if you just time things, or even just go for a week or two, or a week, you can watch a rocket go up. And the experience that you have from being at Cocoa Beach is roughly the same as the experience that you have closer up where we had it as journalists. So, if you can get to Orlando and then you rent a car and you drive out to Cocoa Beach and you stand on the beach when the rocket goes off, you will see it, you'll feel it, you'll experience it, and you'll understand just what an amazing accomplishment rocketry is. I'm sure you noticed the Stargate planet name that appeared above my shoulder, and this is a way for you to vote, for you to tell us what you thought was the best question of the week, the best answer of the week, the best combo, whatever struck your fancy. So the winner from last week was S. Morrow. Could we ever work out exactly how many years old the universe is? So thank you everyone who voted. Now we're going to put a different Stargate planet name up above my shoulder with each question, and then we're going to count up all of the votes, and we will celebrate that next week. So we'll put the list down in the show notes down below. And so just wait, watch all of the questions, evaluate very carefully, and then tell us what you thought was the best question. Three Dog 1963. You've said that space launches occur as close to the equatorial region as possible to get an assist from the spin of the Earth. So if the spin of the Earth were faster, launching heavier items would be easier. And conversely, if the spin were slower, it would be more difficult. At what point would the spin be so slow that we would be forever trapped on Earth? So your question is half right. In other words, yes, if the Earth was spinning more rapidly, then you would have an easier time launching from the equator. And this is just because the Earth is turning at a little over 1,000 kilometers per hour. And if you need to go into orbit around the Earth, you need to be going 28,000 kilometers per hour above the equator. And so you've already got 1,000, so you just have to make an additional 27,000 kilometers per hour to then be going in orbit around the Earth. But if the Earth was spinning faster, if it was going 2,000 kilometers per hour, then you'd only need to make up 26,000 kilometers per hour. And if it was going 10,000 kilometers per hour, then it would be even easier. But the problem is at a certain point, the Earth would start to tear itself apart. And so really sort of like the perfect spacefaring nation is the one that lives on a planet that is rotating just shy of completely tearing itself apart. And then you would have the easiest way to get into space. But the second half of your question was like, what if you went the other way? And what if you slowed down? Well, no, there is no slowest speed. That if the planet was not rotating and you still wanted to go into orbit, then you would need to go 28,000. You have to pay the full fare of going into space. And we see versions of this all the time. Most of the time, you don't care where your rocket is going. You launch at the equator in the direction that the Earth is going. You just take advantage of that. And so if you've got a communication satellite or a weather satellite or a space station, that is the least expensive option. And so you take it. But if you are interested in your orbit, then sometimes you have to decline the discount. And so a good example is, say, a polar orbit. So when you think about the Earth and it's turning, and if you've launched from the equator and now you're going around the equator, and you can launch at a bit of an angle, so you're going a little bit above the equator, a little below the equator, then as the Earth is turning underneath you, you're going to see different parts of the Earth up to a maximum latitude above or below the equator. But there's going to be parts that you're just not going to be able to see. But if you launch on a polar orbit, that means that you're now launching towards, say, the North Pole or the South Pole. And you're now going, if the Earth is turning, you're going around the Earth like this. Now the Earth is going to turn underneath you, and so you're going to get a chance to see the entire planet. So that's a much better perspective for being able to view all of Earth. And you can sort of time things so that the same spots of the Earth appear on a regular interval as you're doing this polar orbit. But the price you pay is you have to pay the full ride. You don't get that 1,000 kilometer per hour discount. You've got to pay the full 28,000 kilometers per hour, which means either more rocket fuel or a lighter payload to be able to go into orbit. And you can even go in the opposite direction. You can go against the orbit of the Earth, but now you've got to pay an extra 1,000 to go in a retrograde orbit. So, yeah, that's how it works. Chris Terrell, live active. Fraser, could you do a video on the setup you use to photograph or video auroras? I'm not the guy to give you detailed tutorials on how to photograph auroras. I've done my share of aurora photography, but I'm by no means a professional. But I'll give you some quick tips. So we're at the point now in the modern technology where just your smartphone does a pretty good job of capturing an aurora. And a lot of the times when there is aurora activity and it should theoretically be visible in your area, and you go outside and you look to the north and you don't see anything, if you want to know if there is actually aurora activity, take a picture with your phone. And with the new iPhones, with the new Android phones, they're pretty good in low light and doing fairly long exposure photography, especially if you have a little tripod for it or you prop it up against something when you take the picture. It'll go for 10 seconds, 20 seconds, just try and do a long exposure image of the sky. And if you can't see the aurora with your eyes, but the phone may show it up. So I'm going to share a couple of pictures that I took on my recent trip to Iceland, and we could definitely see the auroras, but they were like a hazy green cloud in the sky and not with the purples and the pinks that you're seeing in this picture. So that's the first thing, is just use your phone. If you want to go to kind of like the next level, then you need to get like a DSLR camera. And then you need to be able to take you need to be able to take exposures of the sky. And the trick with auroras is that the length of the exposure that you're going to need to do to kind of take a picture of the aurora kind of depends on the strength and the level of the activity of the aurora. And people who have taken lots of pictures of auroras know exactly what I'm talking about, that there can be the kinds of auroras where it's just this sort of shimmering glow that's off on the horizon, and you'll do a 30-second exposure or a minute-long exposure, and what you get is kind of what you see, but better. But there are other auroras which are alive, that they are changing like writhing snakes in the sky, and that if you try to do a long exposure of 30 seconds or a minute, you just get this green mash that doesn't capture what it is that you were seeing. That in many cases, it's the shorter exposures that are the ones that are going to really kind of reveal the features and the details of what you saw. And so I'll share another video that I took. And in this case, I was doing very short exposures, and then I was turning them into the frames of a video. And that much better captures what we were seeing. But still, it's not quite what it's like to actually watch an aurora with your own eyes, or to watch a strong aurora with your own eyes. And I've never seen a video or image that captures it accurately, just because, like, I'm sure if like a really good camera that can handle really low light and it just shot at 60 frames a second and tried to just capture the aurora, maybe that'll get you there. But there is just something to be said for watching these things with your own eyes. And so if you're trying to set up to take photographs, be ready to put your camera down and just take it in with your eyeballs. Good luck. Mark Scales, how big is the solar system? That's a great question. And it really sort of depends on what you define as the solar system. Where does the solar system begin and where does the solar system end? So let's talk about a couple of ways you could measure it. So you could say, okay, the planets are the end of the solar system. And that, you know, with Neptune being the most distant planet, you're in a few billion kilometers away from the sun. But then you could say, well, no, like there's the Kuiper belt and there's all of that stuff. So now you're sort of farther away. Let's switch to astronomical units, where each astronomical unit is the distance from the Earth to the sun. And so the Kuiper belt is out in the 60 to 100 astronomical unit range. And yet we know that the Voyager spacecraft have passed outside of the heliopause. And so when you think about the solar wind that's coming off of the sun, you've got these charged particles that are blasting out into space. But this is happening from every single star. And so there is this point where all of the collective solar winds from all of the stars in the Milky Way are bumping up against the solar wind that's coming from the sun. And because, you know, it's closer to the sun, it's more concentrated, it has a stronger force, but eventually you reach this point where the interstellar wind is stronger than the stellar wind, and that sort of defines an area, and that's called the heliosphere. And we know that the Voyager spacecraft recently exited the heliosphere, and it's a little farther than the Kuiper belt. So that's another way. And so you'll hear these things like, oh, the Voyagers have left the solar system. Well, not exactly. They've left the heliosphere, but they're still in the gravitational dominance of the sun. And so sort of the next thing you can imagine as a way to describe the size of the solar system is the Oort cloud. The Oort cloud is this giant collection of icy objects that extend out for tens of thousands of astronomical units away from the sun. So you can measure that in terms of light years. It's believed that the Oort cloud could extend as far out as like 1 to 2 light years away from the sun. And when you think about how, if the same thing is happening at Alpha Centauri, extending out 1 to 2 light years away from Alpha Centauri, and Alpha Centauri and the sun are 4.5 light years away from each other, well, our Oort clouds are getting close to actually touching. So that is sort of a good way to describe the size of the solar system. I think when I really imagine the solar system, I think you got to include the Oort cloud. So now you're out 1 to 2 light years away from the sun. But as we've talked about in previous videos, that you could be under the gravitational influence of the sun across the entire observable universe. You could be 46 billion light years away from the sun. You could see the sun in your telescope and you would be experiencing the gravity from the sun. So are you still in the solar system? So you're just gonna have to decide where you think the solar system ends based on the stuff that I provided. Red Streak 1. How hard would it be to do a sample return from Europa, ignoring planetary protection concerns for the moment? It would be incredibly hard, but not impossible. So, let's think it through. So in order to get to Europa in the first place, you would need to send a spacecraft, and the Europa Clipper just launched, so we can use that as an example. The Europa Clipper is the most massive interplanetary spacecraft that has ever been flown. It's 6,000 kilograms. It took a Falcon Heavy, which is one of the heaviest lift rockets that we have today. That wasn't even enough speed. Like, the Falcon Heavy can't on its own get Europa Clipper to Jupiter. It'll have to do a flyby of Mars and then a flyby of Earth to get gravitational assist so it can be on the way. And then a lot of the mass of the Europa Clipper is propellant for it to, when it finally reaches Jupiter, to be able to put itself into the right orbit to be able to go around Europa. So let's say that that's your mission. You've sent this mission to Europa. Okay. Now you've got to have a lander. You got to get down to the surface of Europa. So in addition to the orbiter that you sent to Europa, you're going to need several thousand kilograms of lander. And that's because the lander isn't just a lander. The lander also has an ascent module. In other words, the lander is going to be able to get down to the surface of Europa. And then when the samples have been delivered, they're going to be able to go back onto the ascent module, back up into orbit. And then you're going to need to be able to come home with them with some kind of return mission. So, above and beyond the orbiter, you're going to need to be able to fly back home to Earth. But the samples aren't sitting there on the surface of Europa. They're going to be underneath tens of kilometers of ice that you have to get through. Okay, so now there's a lot of people have proposed really interesting ideas on how you might be able to get down through that ice. You would have some kind of melt probe where you've got a decaying chunk of plutonium in the front of a thing that looks like a dart, and the thing aims down, and the plutonium makes the front end of this probe very hot, and then it melts the ice in front of the probe, and the probe starts to sink down into the ice. And this has been tested out. Like, people use this as a way to go under the ice in places like Greenland, like at meters per minute. It's actually quite an effective way to get under the ice. So you have a scaled up version of this. It might take you a couple of years to slowly melt down through the ice until you finally reach the water down below. And you have been spooling a wire that is then frozen into the tube that you have melted behind you. And so now you deploy little robots that collect samples, and you're probably going to want samples from different places, not just the water right at the surface. Maybe you want to go all the way down and see if you can find black smokers or some kind of potential life. And then you bring those back to the probe. And here's the hard part, which is getting back up through the ice. And so to get down into the ice, all you had to do was use gravity, which would pull you down through the ice and melt behind you. But now you have to go against the gravity to climb up through tens of kilometers of ice. So maybe you've still got that plutonium that is in the bottom of your probe, and then you have to shift it up to the top so that now you're melting above you. And now you need some way, whether you can you can gain electricity from the decaying plutonium like the RTGs that we see on various spacecraft, so that you can start to climb up the inside of this tube that you have already dropped down. And I don't even know how that would be done. That is the hard part, is getting back up. And so then you're able to, but maybe you could float, as you liquefy the water and you maintain less pressure, you would float and stay at the top of the water. Maybe that would work. You remain buoyant and you would just keep floating up this column of water that you're creating. And then you would reach the top, and then you would pop open the top of your spacecraft. You would deliver the samples to the ascent module. The ascent module would take off from the surface of Europa. It would meet with the return capsule, and the return capsule would fly home to Earth. It would descend through the Earth's atmosphere, would land in the desert, probably Utah, and people would take it to a sealed facility, and they would open it up, and they would learn a tremendous amount about what is under the ice on Europa. But the other place in the solar system that would make this a lot easier is to go to Enceladus. Enceladus is one of the moons of Saturn. At Enceladus, this water is spraying out into space. And in theory, if there are biological chemicals in that ice, you're going to be able to detect it. And you could detect it in situ. You could sort of smash your spacecraft into the ice and lick it, taste it, and that would tell you whether or not there's life there. But also you could pass through, collect samples, and you didn't even have to go down into a gravity well. And then you just fly back down to Earth and return those samples. So that's why we're going to see a sample return mission from Enceladus long before we see a sample return from Europa. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: John Deward, Paul Carr, Yvonne, Peter Oberle, Stan Spanish, Jamjari Weol, Tricor, Brandon Lee, Daniel, Kevin Sheridan, Stephen Gearhart, and Daryl Stewart. Join the club at patreon.com/universetoday. Shard, why are we worried about contamination from probes? Wouldn't any microbes die in the vacuum of space? Oh no, this is one of the horrifying discoveries that we have made, and that is that Earth life is incredibly resilient to the most hostile environments we can possibly imagine. So there are experiments on the outside of the International Space Station. There are these boxes that have little sample capsules inside of them, and they will open up these doors so that the sample capsules are just exposed to the hard vacuum of space. And then various life forms from Earth, so cyanobacteria, archaea, mosses, lichens, of course tardigrades, those hardy water bears, and other stuff, are seeds, things like that. They are exposed to the vacuum of space for years. So you're in the hot, cold as the space station is going around the Earth and going into and out of shadow. You've got the vacuum. You've got the intense radiation that you're experiencing above the Earth's atmosphere, and the complete lack of any kind of water. And then they bring the samples back down to Earth after a couple of years, and then they see how well the life forms did. And some are killed, but others, like cyanobacteria, tardigrades, they just wake up. You bring them back to Earth conditions, they wake up and get right back to what it is that they were doing, as if they didn't even notice. And the cooler version of that experiment is they have also brought those life forms awake in Mars-like conditions, and where they do still have access to water, and found that in fact these microbes can handle living on Mars. And so when we attempt to sterilize a spacecraft, we can only do so good of a job. You can take a spacecraft, you can take every single part in the spacecraft, and you can bake it in an oven at hundreds of degrees. And then you can put together your spacecraft in a hermetically sealed room chamber that has no air coming into it. And then you can put it into your rocket fairing and you can launch it to space, and it will still have bacteria, Earth life. And some of that life is the kind of stuff that can handle the journey to Mars and thrive if it can find the right conditions on Mars. And so, we don't know if there are deposits of liquid water. There could be like patches of brine that are on the surface. And if life from Earth could find its way into some of those patches, it could conceivably grow. And if there's any indigenous life in those areas, then it would have to compete with Earth life. And it really feels like the Earth life, which has had like a lot more energy, a lot more evolution going on, it won't necessarily have the same adaptation, but we've seen here on Earth that you get invasive species that, you know, the native species just get demolished by invasive species that are well adapted to that environment. So that's why you worry, is that we know that Earth life can survive and thrive in the most horrific conditions and recover. And so any spacecraft that we send out there, if they get to liquid water, then there's a really good chance that we're going to start infecting that water with Earth life. M. Nokel, are there plans to explore lava tubes on the moon or Mars? I toured a massive lava tube in Iceland today, and it had colonies of bacteria in absolute darkness. Trigger alert, I'm going to say the word lava a lot with my Western Canadian accent, and I know it sounds wrong to your ears, but this is how we say the word here in Western Canada. So yes, the various space agencies are really excited about the possibilities of exploring lava tubes on places like the moon or Mars. And there's a lot of really good reasons, really exciting reasons why you would want to go there. And so when you think about what happened, right, in the past, you've got some kind of volcanic event, you've got flows of lava that are coming down the side of some shield volcano, and it gets this crust that forms over top of it. And then the lava keeps going, and in many cases, it will sort of completely vent out and leave the chamber that it has created underneath. And when you've got much lower gravity, the sizes of these chambers can be a lot larger. So while on Earth, you know, maybe a lava tube is going to be tens of meters high, on the moon, it could be hundreds of meters, kilometers high. You could hide a whole city inside a lava tube on the moon. And so from just a protective place, they're incredibly useful, because if you set up inside a lava tube, then you're going to be protected from the radiation that's coming from space, that the temperature is going to be a lot more regulated. You're not going to be going through this hot and cold back and forth. And you also get this historical geologic record of the history of the moon inside the tube. And so there's like a lot of really good reasons. And you don't just have to sort of crack through the top of one of these tubes and spelunk down. There's a lot of places where you've got the exit point of that lava that I mentioned. And so there's going to be like a cave that you can just walk in and set up your base inside on the moon and on Mars. But we do see these lava tubes from space. You've got spacecraft that are orbiting around the moon and Mars. We can look down and we can see what they're called skylights, these collapsed tops. And very recently, the Lunar Reconnaissance Orbiter was able to do some mapping of the interior of one of these tubes and sort of get a sense of the true scale and shape of, you know, and obviously it couldn't see as beyond sort of just peeking down one of these skylights. And then on Mars, it's even better, because, you know, you could have conditions where you might even have, say, briny water that is able to handle being in a low pressure environment, a very cold environment, when you're sort of just down in this lava tube. And then these are the places where you might find evidence of life on Mars, either past or present. And so they are like really much better, more safe, protective places to be able to explore. And then at the same time, though, they are scientifically fascinating, the most scientifically fascinating places that you could go to those worlds. And so they are huge priorities for every space agency. Jay Passer, do we know how strong or weak the wind on Titan is? Yeah, we do. More or less. So when the Cassini-Huygens mission arrived at the Saturn system, the Huygens probe detached and flew down through the atmosphere of Titan. When it was passing through the upper part of the atmosphere, it was experiencing winds of about 430 kilometers per hour. So that's really fast. But then as it got closer and closer to the surface, the wind speed slowed down and it wasn't moving very fast down at the bottom. But recently, astronomers have been looking at the seas on Titan. You know, we know that there are these oceans and seas of liquid methane on the surface of Titan closer to the poles. And they think that they were able to detect waves in these seas. And of course, you can't have waves without wind. And so there must be some kind of surface wind that is pushing this liquid methane around on the surface of Titan. And the waves are a couple of meters high. So theoretically, you could surf them, which is pretty cool. Now we're going to get conclusive answers to this and many questions about Titan when NASA's Dragonfly mission flies to Titan. It's going to be launching in 2026, which is just 2 years from now, but it's not going to get there until 2034. But it will get there. So just distract yourself with video games, and books, and movies, and TV shows, and then you'll look up and wow, Dragonfly will be on Titan, and then the fun can begin. And if you're not familiar with the Dragonfly, this is a nuclear-powered quadcopter, a helicopter that's going to be flying on Titan. Ronald Big Money Anderson. Don't they need legs to land on the moon or Mars? When will we see legs on Starship? Yeah, so with Starship landing on Earth, they're not putting legs on it, that it's going to get caught by Mechazilla in the same way that the Super Heavy booster was caught by Mechazilla. And that saves them a bunch of mass, and that means they can use less propellant or have larger payloads that they can send into orbit. But when they go to the moon, they will absolutely need some kind of landing legs at the bottom of Starship. But the good news is that on the moon, the gravity is 1/6 of what it is on Earth. And so the material strength that would be required to support the weight of Starship would be 1/6 of what it would be on Earth. And it would be 1/3 of what it would be on Earth if you were on Mars. So they will need landing legs, but they will be smaller than what they would be to try and support the weight on Earth. Now, that said, if we ever get to a point where there is significant infrastructure on Mars, you can imagine, or on the moon, you can imagine these spacecraft not having legs, that they arrive and there is a Mechazilla waiting for them on the moon or Mars, and it captures them and puts them down gently. And this is we are building infrastructure for becoming a solar system spanning civilization. Grail C, what do you think is the chance of Europa Clipper finding plumes and sampling them? I mentioned that question about getting a sample from Europa, that a better place to go to get a sample would be Enceladus, because we know that there are these geysers, plumes, blasting water ice out into space. But it's possible that there are these plumes at Europa as well. They have been theorized. There has been sort of some people thinking that they've found them and other people thinking that they haven't found them. But Europa Clipper will definitively tell us whether or not there are plumes and geysers at Europa, just like there is at Enceladus. Well, it won't be as extreme as Enceladus. Like, we know that. But if they are, Europa Clipper isn't equipped to detect the presence of life in the way that a dedicated mission that was designed to fly through the plumes of Enceladus or the plumes at Triton are. But it would still have a pretty great suite of instruments. And so you can imagine it flying through the plumes or close to the plumes and measuring the kinds of chemicals that it sees in the plumes. It would be looking for organic molecules. It'd be looking for the presence of things like hydrogen gas, which is food for bacteria. It'd be looking for the presence of carbon, nitrogen, phosphorus, other chemicals that life might need. And, maybe you could even start to detect more complicated things like methane, ethane, ammonia, various things in those geysers. So no, like Europa Clipper just isn't equipped to detect the presence of life in plumes, but it could detect the plumes. And then from there, follow-on missions could be custom built to try to answer this question of, is there life under the ice on Europa? And that would be an easier mission than to try and find out if there's life at Enceladus. It's closer, it's easier to get to, but it may still be that flying through the plumes at Enceladus is our best chance. Like if I had only one chance to search for life in the solar system, it would be to fly through the plumes of Enceladus, because we know there's hot water under the ice that's in contact with hot rock it contains all of the raw material that life requires. The question is just, is there life in it? Nunya business. Any news on Starshot? So the Breakthrough Starshot, this was the project that was announced several years ago where people want to research using a laser sail to send a fleet of tiny spacecraft, microsatellites, to Alpha Centauri or Proxima Centauri. This was quite exciting. It's funded by a billionaire, so he's got deep pockets, and a lot of interesting projects rose up to sort of consider all of the various possibilities. But the reality of Project Starshot is that most of this is science fiction. Not Star Trek science fiction, not impossible science fiction, but that we don't have lasers powerful enough to be able to provide that kind of velocity to a spacecraft. We don't have the material science to build solar sails that are that small and that strong. We don't have the miniaturization of the technology to be able to provide that level of intelligence on the satellites. We don't have the ability to aim them and get them in the trajectory that we want them to go. So there is just an enormous amount of technological development that needs to go into this. And it is not like all of humanity is obsessed with this one goal. When you think about the three-body problem and the sort of single-minded obsession of the Trisolarans, when you think about Project Hail Mary, and you think about how all of the world's resources were channeled to this one task in Project Hail Mary, we don't have that. We have a billionaire who is funding a bunch of scientists and engineers to work on some ideas, but we are just so far away from the technological readiness to start to consider this. But, you know, we discuss in bits and pieces here on the channel, and I do tons of interviews with people because I'm obsessed with this topic as well. You know, we do interviews with people who are thinking about, oh, like, what would be the best way to communicate with all of those probes, or what would be the best place to put a laser so if we wanted to fire it and not cause damage to Earth, where should we put it? What are some possible materials for the solar sails that would make a lot of sense to be able to both provide the strength when you're getting hit by the laser and not just melt, but also provide the acceleration that's required to get the spacecraft up to 20% the speed of light. So, like, I want you to manage your expectations that we are likely many decades away from practical prototypes of this kind of technology actually being tested. And we're going to see it tested here in the solar system. You're going to see tons and tons of lasers. Like NASA has launched a solar sail and is now starting to operate it. And that's not like a laser sail. It's not miniaturized. It's literally just, can we make a solar sail work? So no one has tested laser sails in space yet. So there's just a huge stack of technology that needs to be done. So, you know, I will bring you every single iteration of this technology as people develop it and work on it and obsess about it. And, you know, you will watch the entire history of humanity's exploration of interstellar space in real time here on my channel, but it's going to be too slow for what you want. And I know that. I mean, I've been doing this job for 25 years. Did you think that 25 years ago, I would be still waiting many years for people to go to Mars? No, it was going to happen. You know, I read the case for Mars. It was going to happen within a couple of years. And yet here I am, old, gray, you know, ready for retirement. And it still hasn't happened yet. So I'm not going to retire. Don't worry about it. All right, those are all the questions that we got this week. Thank you, everyone who put your questions into the YouTube comments. And thank you, everyone who joined me for the live show that we record every Monday at 5 p.m. Pacific time here on YouTube. Of course, we are going to be mixing things up shortly. We're going to be having some episodes be for people in North America, some episodes for people who live in Europe, and some episodes for people who live in Asia and Australia. So stay tuned. The actual live event times are going to change slightly. Now, I'm going to talk about a really exciting development that we're going to be bringing back. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Barry Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, Spiderswap.io, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all of our patrons, all your support means the universe to us. So one of the questions that people have been asking me many times is, when are the virtual star parties going to come back? And my answer has been that they're probably not going to come back. And that is because it is just always so complicated and difficult to be able to wrangle astronomers, to be able to coordinate people's times. You have bad weather and gear and all of that. And it just, burned out anybody who volunteered to try and coordinate this activity. Well, we've got a new solution, which is our good friends at Starfront are going to provide us with a telescope and a mount. This is a telescope co-location where you've got tons of telescopes in one of the most pristine dark sky places in the world. And they're supplying a really powerful telescope. It's a Celestron Origins telescope. And if you've never heard of it, this is sort of like a really fancy smart scope that is able to take really good pictures of the night sky very quickly. And we've been doing a bunch of tests. I'm going to show you a couple of the pictures that I've been doing. And keep in mind, these are just test shots, the kinds of things that I was capturing in 30 seconds, 90 seconds, the kinds of stuff that we could show live, the comet, the moon, various nebulae, galaxies, things like that. And so with almost always having clear skies, access to a powerful telescope that we're going to be able to use, we now have a really firm foundation for being able to bring the virtual star parties back. And then we can layer on top of that guests and other telescopes and friends and celebrities and people who want to experience the night sky. And so thanks in advance to Starfront for being able to help make this finally a reality. And I am so excited about what we're going to be able to do from here on out. So stay tuned for upcoming virtual star parties. And it might even be by the time you watch this, we have already done one. All right. Thanks everyone. And we will see you next week.